Hi guys. So today we're gonna be solving geometrical problems for kids. Yeah, let's get started. So um, today's problem is quite famous, although it was taken from a list of problems proposed by this guy. There will be like a photo of him. He's pretty smart. If someone doesn't know, his name is Arnold. Yeah, he's from Soviet Union. So, and the list he proposed was for kids who are from 5 years old to 15 years old. And in that, like, from his words, kids of that age, they are supposed to prove that problem. And let's get started, I guess. So the problem itself is related to the triangles, as we can see. And the main idea is basically we have like the main triangle ABC, right? And on the each side of the triangle we make another triangle with the same sizes, right? So yeah, the main idea is that if we connect the centers of those equilateral triangles that are constructed on the sides of the main triangle, we'll get another equilateral triangle, that would be like a fifth triangle in our picture, basically. So if we connect them again, all the time, no matter what the initial triangle is, we'll get the equilateral triangle. And so first, again, I think we need to make certain constructions and like think about the picture a little bit more. By the way, so the proof itself is like it's basically mine. I haven't like looked at any like solutions available on the internet, so I'm not sure if that's the easiest way to solve the problem. And yeah, the problem itself, we need to prove that that's always true. So yeah, I would be glad to see like other proofs, like maybe easier ones. But I think my proof is based on a pretty straightforward idea. That's like also pretty important for geometry as well. So yeah, let's get started. So the main idea of my proof is that we'll be moving or like rotating the triangle around its like a certain point. So in this case, as we can see, we have our triangle, like initial triangle, and we just rotated it around its center. So here it's like 40 degrees, but I'm not sure, it's just like as an example. Another case where we can choose the rotation point is the vertex is the like point on the side of the triangle, or like it can be like outside of the triangle, and that's completely normal. So the main idea of my proof is that we will be just rotating the picture, and the point of that is we know that the triangles constructed on the sides are equilateral, and one of the main properties of those triangles is that each angle is 60 degrees. So basically, the equilateral triangle, if we draw it, and for example, rotate it around the center, 60 degrees here, 60 degrees here, and 60 degrees here. And if we rotate it around its center, nothing will change. It will be like the same triangle basically. So that's also important. And like in such problems where you're given like a equilateral triangle or like some equilateral shape, you can think about rotations as well, because it's pretty helpful in the sense that if you rotate the whole picture, your shape might not change, but and that can give you some extra information. So let's see how it works in our specific problem. So basically, we have a triangle, and we want to prove that all the sides of the triangle inside, which we want to provide equilibrium, are equal to each other. That's why let's just make a certain reasoning just for like one one pair of the sides of the triangle, and then like we can apply it to the rest of them, and so the problem will be done. So basically, now I wanna rotate my whole construction around this point onto 120 degrees. Why? Now we will see in a bit. So as we can see, we rotated the whole construction around this point at 120 degrees, and as we said before, if we rotate the equilibrium triangle by 60 degrees or 120 degrees, it won't change. And that's why that side would go here, that triangle would go here, that triangle would go here, and that vertex would go here, roughly. And so the next step, we want to do the same thing, but for this vertex. And if we, so yeah, and we have a rotated here as well, right? So this triangle will go, like this triangle will go here. And so if we rotate, if we do the same thing but around this vertex, we can notice that basically, so these are 60, these are 60, these are 60. So the sum of these three angles would be 180, right? And so that would imply basically that this triangle is equal to the to this angle, right? So, and that would mean that this side is equal to this side and this side is equal to this side, right? And so basically we just need to draw this line to make the same construction, but like for this point. Additionally, we need to make a triangle here. Here's a construction. And so we'll get this thing. And so that's why, and we'll get that this triangle is the triangle we want to prove that it's equilateral. So it went from here to here. So we basically got the same triangles by just rotating the initial construction through two vertices. And as we know that the rotation preserves the lengths of the shapes, basically, we can make the following observation. So if we say that this side is A, this side is B, and this side is C, after rotating around this vertex, we would say that this side is A, this side is C, and this side is B, right? Respectively, if we do the same thing for this triangle, we'll get that this side is A, and this side is C, and this side is B. And so we got the complicated construction, right? So let's simplify it and like just take the only thing. So basically, if you look at the construction we actually want and like kind of ignoring the rest of the construction, we'll get like those three equal triangles that are related to each other for the vertices, right? So, and like, let's summarize. So what we just did, we rotated this triangle around the this vertex to 120 degrees. We did the same thing for this vertex. And so, as I said, rotation preserves lengths of the sides of the shape, right? So That's why we call this side A, this side C, and this side is B. And if we rotate it around this vertex, we would see that this side is C, this side is A, this side is B. And same for here, this side would be A, this side would be... Sorry, no, this side would be B, this side would be C. My bad. And if you look at the picture, we actually want to rotate it around this vertex as well, because we have rotation here, and like something is missing here. And so right now it's not like rigorous enough, but like if someone wants to prove that after rotation on this vertex, this triangle would correspond to this triangle, it's basically the same process that we did before, because there's like a equilibrium triangle in between. So yeah, if you want to do that, it's a great exercise. And so yeah, if we rotate around this vertex to 120 degrees, we would see that this side goes to this side goes to this side, and so this side goes to this side. That basically means that C is... let's stop for a second, because I just realized that I messed up the picture and the sides that are called B, C, like they're supposed to be swapped. And it like changes the reasoning a little bit, but like it's not like fatal mistake basically. So he says that C is equal to B, B is equal to A is equal to C. But actually it should be like A is equal to B in that case. And then after we can apply the same whole reasoning that we like done before to the all pairs of the sides, and then we can prove that all sides are equal to each other. That's it. Yeah, why does it matter? So again, there you won't find any useful applications of this fact. I guess yeah, it's more of theoretical and like interesting construction that just appealing to your eyes, basically. And also, I think it's also a nice exercise for your brain, because you deal with some abstract and like shapes and spaces, and like it makes you to think about the problem. I'm sure there are more than one proof, and like this is not the best one. I'm sure there are like some flaws in it, but the general idea is pretty nice and neat, I think. Also, I got a new mic, as you can see, and the sound is better than in the previous video. And I want to also say thank you to Vladimir Arnold, the smart man who provided this problem to the list of the problems for the kids. So if you guys like this kind of stuff and like proofs and like math and just talking about that would be great. Yeah, just solve math, read books, enjoy life, and see you in the next video, I guess.